Hello, hello, hello. It's been so exciting coming your way once again with making physics easier or simpler with Sir Eric. Yes. In our last meeting, we looked at acceleration of a body in simple harmonic motion. So we've gone through displacement, velocity, and acceleration. Okay. So let's quickly have a recap of these three areas of SHM, and then we take it off with another concept under simple harmonic motion. So a quick recap. All right. So we saw that the displacement function, the displacement equation of a body in simple harmonic motion. The displacement equation is given by y is equal to a sine omega t. That is vibration or oscillation along the y-axis, and x is equal to a cos omega t, that is along the x-axis or the horizontal axis. All right. Yes, so these are the displacement equation. All right, and we observation we saw that displacement is maximum at the extremes, and then it is minimum displacement. So our observations are that displacement is maximum at the extremes. Okay, here at the extremes, and then here we are saying that y is equal to a. Okay, then displacement is minimum at the mean position. Here y so displacement is minimum at the mean position. Here y is equal to 0. When we plot a graph of the displacement at any time t, so t against the displacement, and here in our graph we have, since a complete oscillation is equal to it takes a time of capital T, which is the period. Let's divide the period into a 4 cycle, and that will be into a 4 cycle. Quarter of the period, half of the period, 3/4 of the period, and then one complete cycle. Okay, let me adjust the screen a little bit. Good. So we are dividing the full cycle into the time taken to make a complete revolution into parts, quadrants. Okay. Then our maximum displacement is the amplitude. So this is A. Since we have two different amplitude, one up and one down, this is minus of A. Minus of A. Now, at a time t is equal to 0, what is the displacement? The displacement is 0. At a time t is equal to quarter of the period, the displacement is equal to the amplitude. So here, this is what we have. So at a time t is equal to quarter of the period, okay, the displacement is equal to A. At a time t is equal to half of the period, the displacement is this. At a time t is equal to 3/4 of the period, the displacement is equal to negative of the amplitude. And then at a time t is equal to period, capital T, the displacement is equal to 0. Okay, so when we join the point, we have this. Yes. So this is the graph of the displacement for one cycle. For one cycle. So for one cycle, we have y is equal to A sine omega t. So this is the displacement of the cycle for one cycle. If the motion continues, you will see a repetition of the same values. Okay, 0, A, minus A, repetition, telling you that this motion we are considering is harmonic. Harmonic motions are repeated motion. Okay, so this will be the displacement graph when we are considering a vibration along the vertical axis for one cycle. Let's look at when the graph, when we are considering vibration or oscillation along the x-axis. So oscillation along the x-axis. Along the x-axis. Along the x-axis, the displacement x is equal to A cos omega t. So we are considering displacement along the x-axis. X is equal to A cos omega t. So let's divide the time taken, the time for a complete oscillation is the period capital T. So we are dividing the period into quadrants, okay, or different parts. Quarter of the period, half, 3/4, and then so the vertical axis will be for our displacement x. The maximum displacement is equal to the amplitude. Since there are two different amplitude minus A. This is quarter of the period, half of the period, so this is 3/4 of the period and then a full period. So at a time t is equal to 0, t/s, at a time t is equal to 0, since cos 0 will be equal to 1, okay, it will be equal to the amplitude, positive. Cos 0 is 1, so x will be equal to the amplitude. At a time t is equal to quarter of the period, the displacement x will be equal to 0. At a time t is equal to half of the period, the displacement will be equal to minus A. Minus A. At a time t is equal to 3/4 of the period, the displacement will be equal to 0. And at a time t is equal to the period, the displacement will be equal to A. Equal to A. Let me trace it well. So when we join the point, we have showing that this is a cosine function. X is equal to A cos omega t. Okay, now this graph, these two different graphs, the displacement along the x, displacement along the y, establishes the difference between a sine function and then a cosine function. A sine function always starts from the origin 0, whereas a cosine function always starts from the amplitude, the maximum value of the vertical coordinates. Is that okay? And so this is it. This is a graph of a displacement function along the x, y axis and along the x axis beautifully. Alright, so this is all the nitty-gritties we recapped on displacement. Let's look at velocity. Since the body is continuously being displaced, meaning the body does so with some speed or velocity, and we realize that the velocity is equal to how the displacement changes with time. And along, this is along the vertical axis. So we had the velocity function to be equal to omega E cos omega A cos omega t. This is the displacement function. This is the velocity function. We got this to be the velocity function. In terms of time. Okay, the velocity function in terms of time gave us v is equal to omega a cos omega t. All right. Then we also made some findings here. Where do we have the maximum? Okay, so from here we also derive the velocity function in terms of displacement. Velocity function in terms of displacement. Let me write it here. So we had v is equal to omega square root of a squared minus y squared, and this so v is equal to omega. Okay, give us the velocity equation or function. Velocity function in terms of displacement y. Okay, now here we realize that v maximum velocity occurs when v max occurs when the displacement is equal to 0. So this is omega a squared minus 0 squared, because here we have y being equal to 0. If y is equal to 0, then our maximum velocity is equal to omega times the amplitude. So this is the value of the maximum velocity. So v max is equal to this. Now we also realize that the minimum velocity is equal to 0, always equal to 0, and occurs when y is equal to a. The displacement is equal to the amplitude. Okay, that's the condition where we obtain minimum velocity. Okay, so minimum velocity when y is equal to a, then it means the displacement is equal to the amplitude. Now let's draw a graph of time against velocity. So this is v meter per second. This is time. So we are considering one complete oscillation. We are considering a complete oscillation, and so the time for a complete oscillation is the period. All right. So this is equal to the amplitude, and we have this to be the amplitude. Where is it? Omega a, or a omega. We'll have another amplitude down here, minus a omega. Okay, t on 4, t on half, 3/4, and t. So when t is equal to 0, what is the velocity? When t is equal to 0, the velocity is maximum. When t is equal to quarter of the period, the velocity is 0. Okay, when t is equal to half of the period, the velocity is equal to the amplitude at the opposite end. So we have this. When t is equal to 3/4 of it, the velocity is 0. And when t is equal to the period, big T, the velocity is equal to the amplitude at the upper end. So when we join the points, this is what we have. So this is the velocity function. The velocity function, but this is oscillation along the y-axis. Oscillation, the velocity function along the y-axis. We'll look at the velocity function along the x-axis so that we can compare the two. This is similar to, yes, the velocity along the, okay, so A omega is the amplitude, and the amplitude can be obtained from here.